Hey there, and welcome to The Explainer. Today, we're going to demystify the invisible rules that govern, well, absolutely everything around us. Have you ever looked at a massive 1,000-ton steel ship and wondered how on earth it actually floats? Or why a tiny spanner can loosen a bolt that you couldn't budge with your bare hands? It's all about forces. In this session, we're building it all from the ground up. We're starting with solid, rigid objects and scaling all the way up to the wild, complex behaviors of fluids. Get ready, because we're about to completely change how you see the physical world.
Okay, so here's our roadmap for today. We're kicking things off with the turning effect and finding equilibrium. After that, we'll look at density and solid pressure, which is going to set us up perfectly for our grand finale, Archimedes' principle. Let's get into it.
Section 1, the turning effect. Okay, let's dive right into this and look at how forces actually make things spin.
Now, before we can even talk about turning an object, we have to know where its weight is actually located. And, in reality, the weight of any object is spread out across billions and billions of microscopic particles. But trying to map that out mathematically, total nightmare. So physicists use this brilliant little cheat code. We call it the center of gravity. It's essentially just one specific point where we can pretend the entire weight of the object is acting. For a perfectly uniform object, it's literally just the dead center. Treating weight as a single point like this, it makes everything we're about to do so much easier. So check out this spanner. This is how we actually calculate a turning force, or what physicists call a moment. The moment of a force is just its turning effect around a specific pivot. You can see someone pushing with 30 newtons of force to turn that nut. But, and here is the massive trap people fall into, the force is coming in at a 20-degree angle. You cannot just multiply the force by the length of the spanner. No way. You absolutely must use the perpendicular distance from the pivot to the line of the force. So, if we take that 0.25 meters and multiply it by the cosine of 20 degrees, we get our true perpendicular distance, 0.235 meters. Multiply that by our 30 newtons, and boom, we get a precise moment of roughly 7 newton meters. Now, we really need to distinguish between a standard moment and something called a couple. Because trust me, they are super easy to confuse. A single force applied to an object, like imagine kicking a football, it produces rotation, sure, but it also produces acceleration, right? The ball goes flying across the pitch. A couple, on the other hand, is two parallel forces equal in size but pulling in completely opposite directions. Think about turning on a tap. You push one side away, you pull the other side toward you. The tap doesn't suddenly move across the room, it just spins in place. That pure in-place rotation, that is the absolute hallmark of a couple. Section 2, finding equilibrium. All right, so that covers how to make things rotate, but what if we want things to stay exactly where they are? Okay, for a tiny point object to stay perfectly still, the overall force just needs to be 0. Easy enough. But for real-world objects, bridges, buildings, the phone you're holding right now, there are 2 strictly enforced rules for perfect equilibrium. First up, the resultant force has to be 0, meaning it's not going to slide or accelerate in any direction. And second, the resultant torque, that turning effect we just talked about, also has to be 0, meaning it won't suddenly start spinning. Basically, it's a tie. Neither linear nor rotational forces can win. So the crucial point here really comes down to the principle of moments. For any object to be in equilibrium, all the clockwise turning effects have to perfectly balance out all the anti-clockwise turning effects. Just look at this uniform meter rule. We've got a 1.20 Newton weight pulling down at the center and a 1.50 Newton weight hanging off the left side. By setting those clockwise and anti-clockwise moments equal to each other, we can mathematically pinpoint exactly where that pivot needs to go to keep the ruler perfectly flat. It's like this beautifully precise mathematical seesaw. We can actually visualize this balance using vector triangles too. Take a look at this tethered helium balloon. It's getting pushed sideways by the wind, right? So it's dealing with upthrust, wind force, and the tension from its tether cable. If we draw those 3 forces as arrows, something kind of magical happens. Because the balloon is completely still, because it's in equilibrium, those arrows form a perfectly closed triangle. Notice how the arrows just flow continuously in the exact same direction around the edges? If there was even a tiny gap, or if 2 arrows pointed at each other, that balloon would be accelerating away. Section 3, density and solid pressure. Okay, we've mastered levers and pivot points. Let's zoom out a bit and see how forces act across entire surface areas. Right, so here are the core formulas for how matter interacts with surfaces. Density is pretty intuitive. It's just an object's mass divided by its volume, measured in kilograms per cubic meter. But I want you to really focus on pressure. Pressure is the normal force exerted per unit area. And here is where people almost always get tripped up. They think pressure and force are the exact same thing. They absolutely aren't. Force is a vector. It has a very specific direction. Pressure, though, it's a scalar quantity. It just exists at a point or across a surface without pointing in one specific direction. To ground this in reality, we measure pressure in standard SI units called pascals. Now, 1 pascal is actually super easy to visualize. It is exactly 1 newton of force pushing normally, meaning dead on at a 90-degree angle, spread out over an area of exactly 1 square meter. Honestly, it's a pretty tiny amount of pressure in the grand scheme of things, but it is the absolutely crucial building block for our next big conceptual leap. Section 4, Archimedes' Principle. We've got our solid mechanics toolkit all packed. Now for the really fun part. Let's see how these exact same rules unlock the hidden secrets of fluid dynamics. And this brilliantly illustrates what happens the second we drop an object into a fluid. A liquid pushes, it exerts pressure on the sides of its container and on absolutely anything submerged in it. But here's the kicker. That pressure is not uniform. Because water has weight, the pressure fundamentally increases the deeper you go. Just imagine a literal column of water sitting on top of you. The taller that column is, the deeper down you swim, the heavier all that water is, and the more pressure is squeezing against you. So where does the math for fluid pressure actually come from? Let's walk through it because it's actually a beautiful piece of logic. Step 1, we just start with the force, which is the weight of that liquid column above our object, so mass times gravity. Step 2, now we usually know a fluid's density, not its total mass, so we swap out mass for density times volume. Step 3, to find the pressure, we just divide that total force by the surface area. And here's the magic. The area terms elegantly cancel each other right out. Step 4, we're left with this incredibly clean final equation. Pressure equals density times gravity times height, or P equals rho GH. The crazy part? The shape of the container doesn't matter at all. Only your depth, the fluid's density and gravity dictate the pressure. And this relationship between depth and pressure creates something absolutely mind-blowing. Upthrust. Think about a box fully dunked underwater. We just established that pressure gets stronger the deeper you go, right? So the hydrostatic pressure pushing up on the bottom of the box is mathematically stronger than the pressure pushing down on the top of the box. Since the top and bottom are the same size, this difference creates a net upward force. The water is literally trying to push the box back out. Let's move on and see how this all clicks together into one of the most famous concepts in physics history. Archimedes figured out a way to unite volume, density, and forces into one simple, elegant rule. He realized that this upward buoyancy force, the upthrust acting on anything submerged, is exactly equal to the weight of the fluid that the object shoves out of the way. So let's actually run the numbers on this, because this equation, F equals rho times G times V, is one you absolutely must know. Imagine a 15-kilogram object dropped into a liquid. By taking the fluid's density, multiplying it by gravity, and then multiplying by the volume of the object, we find the exact upthrust. In this specific scenario, the fluid is pushing up with 129 newtons of force. Now, the object's downward weight is 147 newtons, so yes, the object is definitely going to sink, but because of that upthrust, it's going to feel 129 newtons lighter while it does. How cool is that? So from figuring out the exact angle to turn a spanner, to finally understanding why those colossal steel ships can sail across the ocean, it really all just comes back to these fundamental rules: mechanics, balance, and displaced pressure. You are literally surrounded by a symphony of perfectly balanced forces every single day. So I'm going to leave you with this. Take a look around the room you're in right now. If moments, density, and pressure are constantly at play, what invisible forces are secretly working overtime to keep the objects on your desk in perfect equilibrium right this very second? Keep observing, keep questioning everything, and we'll see you in the next explainer.